Welcome to This Explainer. Today, we're going to demystify exactly how engineers predict material failure. Have you ever actually wondered what's happening inside a solid metal bar when it's being pulled or pushed to its absolute limits? We see metal structures all around us every single day. Bridges, buildings, vehicles, and we trust them with our lives. But that trust is built on a really precise understanding of unseen molecular battles. So let's dive right in and uncover the hidden physics holding our world together. To really hook into this topic, we need to think about high-stakes physical failures for a second. A lot of times, people look at an aluminum flatbed trailer bowing under a heavy load or a metal shelf in a warehouse collapsing, and they kind of mash the reasons together. But to an engineer, these scenarios come down to two fundamental, yet completely different concepts: stress and strain. So here's our game plan for today. We'll start by defining stress and strain, then compare normal and shear forces and unpack the famous stress-strain diagram. After that, we'll track elasticity all the way to failure and wrap things up with resilience and toughness. All right, let's jump straight into part one, defining stress and strain. Now, in our everyday lives, stress and strain are, human feelings, right? Like cramming for a massive exam. But in physics and engineering, they are exact calculated measurements of how a body responds to external loads. Imagine a solid metal bar. If we pull on both ends with equal and opposite forces, what we call uniaxial loading, the bar starts to stretch. Stress is the intensity of the internal forces developing inside that bar to resist you, measured per unit area in pascals. Strain, on the other hand, is the actual physical deformation. It's simply the change in the bar's length divided by its original length. And because it's a length divided by a length, strain is actually a unitless ratio, often just expressed as a percentage. And these two concepts, they're forever linked by Hooke's law. If you take the stress and literally just divide it by the strain, you get something called Young's modulus, usually denoted by the letter E. You can think of Young's modulus as a measurement of the springiness of a material. If you apply a force to copper, aluminum, or steel, they all stretch by entirely different amounts. Young's modulus is that unique fingerprint telling us exactly how a specific material is going to behave when loaded. 210 billion. That's 210 gigapascals. That is the Young's modulus of mild steel, meaning it takes a staggering amount of force just to deform it. To put that into perspective, if you have a 20-millimeter bar of mild steel, it won't actually fail until it gets hit with about 79 kilonewtons of force. It's incredibly strong, but as we'll see, it is definitely not invincible. Okay, moving on to part two, normal versus shear forces. To truly visualize these internal limits, just imagine taking a laser and slicing right through the middle of our metal bar to expose the forces inside. There are two distinct types of stress you'll find when you make that cut. First up, we have normal stress, represented by the Greek letter sigma. This acts perpendicular to the surface of your cut. Think of a beam bending, where the forces are either tensile, pulling and stretching the material, or compressive, pushing it together. Then we have shear stress, represented by tau. These are sliding forces acting parallel to the cross-section, which actually deform the angles of the object. You see shear stress all the time in things like bolts. Now, it's worth pointing out that in the real world, a 3D element usually experiences a highly complex mix of both normal and shear stresses, depending on exactly what angle you're looking at. Which brings us to part three, the stress-strain diagram. This graph is basically the holy grail for engineers. They build these empirically in a lab by taking a piece of metal shaped like a dog bone, thicker on the ends so the clamps don't break it, and pulling it until it snaps, recording the stress and strain every single millisecond along the way. Now, if you look at textbooks, you'll often see a graph for engineering stress, which visually seems to dip down right before the material breaks. You might think, wait, how can the stress go down while it's still deforming? Well, actually, scratch that. It's just a mathematical illusion. Engineering stress assumes the thickness of the bar never changes. But in reality, as you pull silly putty or steel, it physically gets thinner in the middle. True stress accounts for this decreasing area. And on a true stress graph, that curve continuously rises until the exact moment it snaps. All right, part four, elasticity to failure. Buckle up because we are going to ride the roller coaster of that stress-strain curve for a ductile material like steel. We've got 5 distinct life cycle phases here as a metal bar is stretched from a slight bend all the way to absolute destruction. The elastic region, yielding, strain hardening, necking, and finally, fracture. Phase 1 is the elastic region. In this linear part of the graph, if you remove the load, the material goes right back to its original shape.
Think of an 18-wheeler driving down the highway with an aluminum flatbed trailer. When it's empty, it actually bows upwards, but when they load it up with heavy cargo, it flattens out perfectly. Take the cargo off, and it bows right back up. It acts perfectly elastic, literally acting like the snap of a fresh elastic waistband.
But if you keep adding force, you hit phase 2, yielding. And here's an absolutely crucial rule to remember. Failure doesn't mean it has to tear in half. Failure just means permanent deformation. We've all had one of those metal slinkies as a kid, right? It's perfectly elastic until your little sibling grabs it, pulls it way too far, and stretches it past its yield point. It's permanently ruined. It never goes back to being a tight coil. To an engineer designing a warehouse shelf, if the shelf permanently kinks and sags under a heavy pallet, even if it hasn't broken in half, it has officially failed.
Now, if you keep pulling past that yield point, we enter phase 3, strain hardening. What's happening inside the steel here is pure molecular trauma. The crystal lattice structure is physically shifting around. The molecules are being dragged out of their preferred harmonious alignment. Because they're now locked out of place and all tangled up, the material actually becomes harder and more brittle. And hey, this isn't always a bad thing. Engineers intentionally use this phase to create things like cold-rolled steel, which is incredibly hard because it's been purposely deformed at room temperature. Finally, we reach phases 4 and 5, necking and fracture. Just like stretching silly putty to its absolute limit, the cross-sectional area in the middle of our sample rapidly thins out. That's the necking part. It simply can't handle the intensity of the force anymore, and bam, phase 5. It completely snaps and fractures in half.
Now there's a super fascinating phenomenon here called elastic recovery. Let's say a steel beam yields. It gets loaded way too heavily and permanently deforms, entering that strain hardening phase. If you suddenly remove the load, the beam doesn't just stay exactly where it is. It will actually spring back slightly. It won't go back to zero, of course, but it will travel back down a line that is perfectly parallel to Young's modulus. Even a totally ruined material tries to give you a little bit of its elasticity back. And that leads us to our final section, part 5, resilience and toughness. You know, engineers don't just look at the line on the graph. They calculate the physical area underneath that curve to design life-saving products. First up, we have the modulus of resilience. This is the area strictly underneath the elastic linear region of the graph. It represents the total amount of energy a material can absorb and still spring back totally undamaged. If you're an automotive engineer designing a car bumper, you want a material with a very high modulus of resilience. You want that bumper to take a low-speed impact, absorb the energy, and pop right back into its perfect original shape like nothing happened.
But resilience is very different from toughness. The modulus of toughness is the entire area under the stress-strain curve, from the very start all the way to the fracture point. It represents the maximum total energy a material can absorb before catastrophic failure. Think about a military bulletproof vest. If that vest gets hit, the engineer does not care if the metal plate yields, permanently deforms, or strain hardens. Permanent deformation is totally fine. The only thing that matters is that it absorbs massive amounts of energy without fracturing and letting the projectile through. It needs maximum toughness.
So, as we wrap up this explainer, I want you to take a look around you. From the chair you're sitting in, to the roof over your head, to the vehicle parked in your driveway. What is the modulus of toughness of the objects keeping you safe right now? Every single beam and bolt is locked in a continuous molecular battle, perfectly calculated to bend but never break. Thanks for hanging out with me on this deep dive, and keep looking at the physical world with an engineer's eye.